happy to introduce the first speaker of the day, Magdalena Larfors, who is going to tell us about string perspectives on manifolds with G2 structures.
Okay, thank you very much. Can you hear me? Very good. So, first of all, I'd like to join all the other speakers in thanking the organizers for a wonderful meeting and for giving me the opportunity to speak. Thank you. I will talk about work that I have done together with some collaborators, which are Senja Dalla Ossa, Eric Svanes, who is here, and Matthew McGill, who is also here. And this work has been published in a series of papers, the most recent one from this spring. So it's quite an humbling experience to talk about these things in front of such an distinguished audience, including some of the forefathers of this subject. So I've taken some comfort in preparing my talk in a quote that you might have seen as you have walked up the main stairs when coming to this lecture hall. So this is a quote from the 1700s, and in Swedish it says "Tänka fritt är stort, men tänka rätt är större," which translates to think freely is great, but to think rightly is greater. So, in this talk, I will present things where we use string theory to think freely about geometry, and hopefully this will lead to some conclusions which we think are right. And I will leave it up to you to judge. So, what we do is that we study compactifications of the heterotic string on manifolds with G2 structure. So this means that we go from a 10-dimensional theory to a 3-dimensional effective field theory. So these manifolds with G2 structure, they are 7-dimensional real manifolds, and I will tell you more about their properties in some minutes. The motivation for this from a mathematical perspective is that by using string theory, we can, as have been done in the past, get new perspectives on geometry, and in particular the deformations of these spaces. There are also tantalizing hints that we might be able to use the results that we find in order to explore things like in topological invariance and other interesting mathematical properties. From physics, the motivation is that we want to determine the effective field theory of heterotic compactifications. And this is something that has been studied greatly for 4-dimensional theories, which arguably describe our universe in a better way. But here, by looking at this less realistic 3-dimensional models, we hope to learn more about how these effective field theories actually work. So that's the motivation. So let me set the scene. We work with the heterotic string, which to first order in the alpha prime expansion is described by the following objects. There are a set of bosonic fields, which will be important in this talk. So there's a metric G, there is a B field, so a 2-form, or up to gauge transformations, B, a dilaton, phi, and there is a gauge field, which has, for a gauge group, which is in E8 times E8. Then there are also fermionic fields, which will play which will not be as important, which are the gravitino, dilatino, and gaugino. Now, when we compactify this, what we do is that we specify that the 10-dimensional space-time decomposes into an external part, which in this case will be 3-dimensional, so 2 + 1 dimensions, and an internal part. And if we want to preserve supersymmetry in this compactification, then we need to have a well-defined spinner on this space, and this spinner has to satisfy a killing spinner equation, which can be written in this form. So there is some connection on the space which has torsion specified by something called the flux, the H flux, and this connection, when acting on the spinner, should give 0. So if we have a situation where we do not have any flux, then this is just the Levi-Civita connection, and we would have a manifold which in 6 dimensions would be Calabi-Yau, and in 7 dimensions it would be a G2 holonomy manifold, so a manifold of reduced holonomy. Furthermore, the heterotic string has this gauge field, which is important in my story, and this is described mathematically by a vector bundle, as is standard, and A here is then the connection of the vector bundle, and this connection has to be an instanton connection. So it has to satisfy an equation which looks like this, which translates into an instanton connection. Furthermore, there is an interesting condition known as the anomaly cancellation condition, which relates the H flux here to not only the exterior derivative of the B field, that should be standard in the type 2 string, but also to Chern-Simons terms for a connection A, so which is this connection here in A times CH, and a connection on the tangent bundle of the manifold. Now, as I have said, in 7 dimensions, the existence of this spinner means that the manifold has G2 structure. So there's a reduction of the structure group. And the goal of this talk is to understand the geometry and moduli of what I will call heterotic G2 systems, which are compactifications on a manifold with G2 structure with a vector bundle for the gauge field satisfying this constraint. Then the tangent bundle has this connection here, which also has to satisfy a similar constraint. And then we have the flux. I should also say that if there are questions at any point, feel free to interrupt.
What is X?
Where is X? Ah, sorry, this should be a Y. Thank you, typo. So the key ideas here, and the result that I will report to you today, is that we can reformulate this heterotic system as a nilpotent differential which acts on a certain bundle, which I will call Q, and this bundle is topologically a sum of the cotangent bundle of the space, the endomorphisms of the tangent bundle, and the endomorphisms of the endomorphism bundles of the vector bundle. And I will show that the infinitesimal moduli can be counted by a Q-valued canonical, a Q-valued cohomology, which is known as the canonical G2 holonomy, and I will describe what this is. I will compare this with the perhaps more well-known 6-dimensional compactifications, the Strominger-Hull system, and this connects to the talk by Lara Anderson that we heard earlier this week. Then I will discuss how we can also describe this system in terms of a superpotential and what use we could have of that kind of description, and then I will conclude and give some ideas for future work. So let me then describe what the G2 structure is. So we have this 7-dimensional manifold. And a 7-dimensional manifold has a G2 structure if there is a non-degenerate associative 3 form that can be globally defined on this manifold. And this is true whenever this manifold is orientable and spin. So this is not a very strong constraint. Then with this 3 form, we get for free a Riemannian metric, which can be constructed directly from this 3 form, and we also get a co-associative 4 form, psi, which is the dual of this 3 form. Now, in compactifications of string theory, in particular in these heterotic compactifications, the supersymmetry constraints will translate into constraints on the exterior derivatives of this 3 and this 4 form, so phi and psi. And this means that the supersymmetry will restrict the torsion of the G2 structure. So what is the torsion? Let me describe that a bit more. So we can decompose the exterior derivatives of phi and psi into representatives, irreducible representatives of the G2 group. So this works as follows. For any 4-form, we can decompose it into a singlet, into a vector, and into a 27-dimensional representation. So here we see that we have the singlet here, which is the torsion part is parameterized by a parameter called tau 0. And then we have the 7-dimensional part, which is given by one form, tau 1. And the 27-dimensional part is given by a 3-form with tau 3 with particular properties. Then we can do the same thing for the exterior derivative of the 4-form. So this is a 5-form, and we get tau 1 again here, and then we get a component tau 2, which lives in the 14 of the 2 forms. And one can show that the supersymmetry constraints of the heterotic compactification gives the following constraints, that tau 0, so this component here, the scalar one, has to be constant. Tau 1, this one form, has to be exact and is specified by the dilaton. And tau 2 has to vanish. And this fact that tau 2 has to vanish will be a very important part in the story. And this identifies this G2 structure as being what Fernandez and Ugarte call an integrable G2 structure. And you will see in the next slide why they have chosen this name. So this is just a bit more description of how you decompose these differential forms. So you do that using the existence of this 3-form so that you can contract and wedge things with the 3-form. So a bit more about the physics. We have these constraints on the torsion, and what one can do is that, so these constraints here, they come from, now let me show. From this condition here. So we can rewrite this condition here as the torsion constraints. This works in the following way, that from the spinner, if we write the spinner bilinear, then we have this 3-form, and hence we can translate this into differential constraints on the spinner. Maybe I should have said that earlier. So we can actually rewrite these constraints in the following way, that d phi is the insertion operator of the flux H on phi. Now we'll define this insertion operator a bit later, but this is a nice compact way of describing these constraints. And d psi is the insertion operator of H on psi, and this way of writing it works whenever tau 2 is 0. And this is also the only case when the torsion of the D2 connection, when there exists a unique connection which has totally antisymmetric torsion. So where we can match the torsion with this 3-form that we have from string theory. And the matching goes like this. So this is actually the expression of H in terms of the 3 torsion classes that remain. So H is specified by the anomaly cancellation condition here. I'd like to think of it as a definition of H for now. Okay, so we see here also that if we do not have any H, then we get D2 holonomy, because then these 2 forms are closed. And one can show that if you have a D2 structure with closed 3 and 4 form, then you have D2 holonomy. So what I would like to start with doing in order to achieve my goal on describing this as describing this whole heterotic system in terms of a nilpotent differential is to encode this geometry here as a differential. And this is something that would be analogous to how you can describe a complex geometry in terms of a Dolbeault differential. So this works like this. Again, what we will do is to decompose things in this decomposed differential forms in terms of irreducible representations of the G2 group. So this was worked out by Reyes-Carrion and Fernandez Ugarte. And what we do is that we define a differential operator D check by projecting onto certain representations. So when it works on 0 forms, it's just a normal D, but when it works on 1 forms, we project to the 7-dimensional component of the 2 form that we get, and when it works on 2 forms, then we project onto the singlet of the 3 forms. And one can show that the vanishing of tau 2 is equivalent to this operator D check squaring to 0, so that this is an nilpotent operator. So this is the reason for the name integrable D2 structure, because this is very similar to an integrable complex structure, and how you describe that in terms of the Dolbeault operator. Because of this, one can write down a differential elliptic complex, and one can define a cohomology related to this complex, and this is what is known as the canonical G2 cohomology. And this will be the backbone of the structure that we will see. And this is, of course, then the analog of the Dolbeault cohomology on a complex manifold. So now we have talked about the geometry, and we also need to talk about the bundle in order to describe the heterotic system. So the bundle has to satisfy this constraint that when we contract it with the 2 gamma matrices, it should vanish. And this translates into this constraint here, that the curvature of the connection should wedge to 0 with the co-associative 4-form psi. And this is the definition of what is known as a G2 instanton in the terminology of Donaldson and collaborators. So we can lift the structure, the canonical G2 cohomology, and the existence of this nilpotent Dolbeault-like operator to bundle-valued forms, and it's very straightforward. I just showed you this on the slide, and you can write down the exactly same thing for an operator dA. So dA would then be it would be D plus A wedge when you act on forms. And you find that this operator here, dA, check will wedge to 0 if you have an integral D2 structure and you satisfy this D2 instanton condition. So our goal is to describe this whole heterotic D2 system, and I've talked about the geometry and I've talked about the bundle, but I also need to talk about the flux here. And the flux is related to this anomaly cancellation condition. So what we need to ensure is that this is also true in our compactification. So we have this constraint here, and if we take the exterior derivative of this, then we get the Bianchi identity, which says that this combination of traces of curvatures should be equal to this exact form here. Okay, I'm sorry. It's something that we need to check. So it's a fact about H then. So from string theory, H here is defined at 0th order in alpha prime as the exterior derivative of B. And then analyzing the formulation of the theory, you find that you need to add these extra terms to the exterior derivative of B in order to get something that is consistent, so that there are no anomalies. Now this is what I said was the definition of H. Now this thing here is something that needs to hold in order for supersymmetry to be true. So combining these two conditions here gives me something that I need to check. And I guess that is the thing that I want to check. I'm sorry, I'm definitely not a mathematician, and my use of terminology can be a bit blurry. I apologize for that. But this is certainly a constraint that we need to, that if we want to compactify string theory, we would need to check it. So if we have some example geometry, we would need to check that this is something that holds. And if we want to describe the compactifications in terms of these nilpotent differentials, then we certainly need to include this constraint here, which relates the torsion to these curvatures here, or the torsion to these Chern-Simons terms. Is something that we need to include in our description. So from a string theory perspective, if you want to compactify something and you want to preserve supersymmetry, then you need to check the supersymmetry conditions, and you need to make sure that all the Bianchi identities are satisfied. You might also worry that there are other constraints that would not follow from the supersymmetry conditions and the Bianchi identities, which would then be related to the equations of motion of the theory. However, for these n equals to 1 compactifications, one can show that the supersymmetry and the anomaly cancellation constraint actually implies these equations of motions if we impose on this connection that I have here on the tangent bundle, which is the connection that appears here in the anomaly cancellation condition, that this is also a D2 instanton. So I will assume this in order not to have to check any other constraints. With that, we have the full description of the heterotic D2 system, which is this collection of 4 objects. Y here is a 7-dimensional manifold with integrable D2 structure. These 2 bundles, the vector bundle and the tangent bundle, have to admit connections, which are D2 instantons. And the anomaly cancellation condition has to hold, which relates the torsion to this exterior derivative of a B field and the Chern-Simons terms. And what I will do next is to find this operator here, which I will call D check, so that this nilpotency of this operator reproduces these constraints. And the operator that we will write down will look like this. So this acts on Q-valued forms, where topologically Q here is this direct sum of the cotangent space, the endomorphism entity Y and V. So you should think of this as acting on a vector with elements coming from these 3 spaces. And D here is, it contains various things that we recognize. So it contains D theta, which is this connection on the tangent space. It contains dA, which we have discussed before. Then contains 2 linear maps, R and F, and it contains an exterior derivative D theta here. So I need to explain a bit what these things are. So d theta here is a connection that we define starting from the D2 connection, nabla H. We can define this d theta, and it will be related to this, but it will have torsion with the opposite sign. So when you write down the connection 1 form for this, you'll see that there will be a switch of indices which corresponds to a change of sign of the torsional part of the connection. Then F and R here are linear maps that map objects, so forms with p-forms with values in the cotangent bundle and V, to p+1 forms with values in NV and the cotangent bundle. So if we take an object from the cotangent bundle, then we will get something which is endomorphism valued, and the definition of the map is this one. And if we take something which is endomorphism valued, we will get something which is which takes values in the cotangent bundle. So these are 2 linear maps. And the next thing we do is that we project in the similar way that we've done before to get an operator D check. So we want to connect to this canonical D2 cohomology and the exterior derivative that is related to that. So we project in the same way. When we act on zero forms, nothing happens. When we act on one forms, we project onto the 7-dimensional representation. And when we act on two forms, we project onto the singlet. And if you do this, and you can just check by direct computation that d check squared is 0, if and only is the conditions that I wrote down a couple of slides ago hold. So what you see from here is that you will get constraints. You will get constraints like d theta check squared has to be 0. You will get constraints which relate how these maps act on various things. And this will only hold if all the supersymmetry constraints hold, and the Bianchi identities. So what I've described here, without many details, is how we can reformulate this heterotic system as a nilpotent differential, which acts on this value bundle called Q. And what I want to move on to next is how we can determine the infinitesimal moduli of this space using this description. So before I do that, maybe I should ask if there are any questions. Fantastic. Okay, so naively, or not really naively, what you would do first is, of course, to look at these different components. So we have the geometry, we have the bundle, and we have the B field. So what kind of deformations do we have in our system? Well, in the geometry, infinitesimally, we can look at the deformations of the 3 form, or that defines the G2 structure. Alternatively, we can look at the deformations of the 4 form, and it turns out that to first order in the deformations, these things they determine each other. And so these are then the geometric moduli. And if there is no flux, then these will be counted by the third de Rham cohomology of the manifold. And this has been shown by Joyce and other people. Been discussed by Joyce and other people. Then we have the deformations of the bundle. So this is, we of course know that if we have a bundle and we look at the deformations of the connection, then the moduli that we have are the ones that do not change the curvature. So this means that the moduli lie in H1 of in the first de Rham cohomology group of the endomorphism valued forms. And then we have deformations of the B field, which will come into play, in particular through this connection to the H flux. So let's think about this a bit more carefully, and in particular think about how this works when we have G2 structure instead of G2 holonomy, so when there is flux. So the geometric deformations, we can rewrite this, so this is the variation of a 4 form, and we can rewrite any 4 form as an insertion operator acting on psi, where M here is a cotangent bundle valued 1 form. And then if we want to preserve this fact that tau 2 should be 0, then we have a constraint on the external derivative of psi. This is why I want to work with psi and not phi. So we have a constraint on the external derivative of psi, which needs to be preserved. And this leads to this condition here, which might be a bit difficult to read. But what it says is that d check zeta of mt, so mt here are the infinitesimal deformations of psi. This has to vanish if we contract it with psi. Then one can go on and explore what the diffeomorphism, so what are the changes that do not change our geometry at all, and these turned out to be describable as the insertion of an exact operated d-check v psi here. So this means that the infinitesimal geometric moduli space that we would talk about would then be given by 1 forms so cotangent bundle valued one forms that would satisfy this constraint, and then we quotient out by these exact pieces, D-check exact pieces. However, this operator here is not an instanton. So this does not define an elliptic complex. This is not something that relates to the canonical D2 cohomology. So there is no reason why this moduli space here should be of finite dimension. It might be in particular cases, but there is no reason. The exception, of course, is if we have D2 holonomy, because then one can show that the torsion part here disappears, and this means that we can rephrase things in terms of this canonical D2 cohomology. So in the case where we don't have a torsion, then this is in fact an instanton, and the story works. So when we have torsion, we need to do something else. And this is, of course, the reason why I'm here. So next thing I want to talk about is the deformations of the bundle. So we see here that the bundle has to be a D2 instanton, and it has to satisfy this condition that connects the curvature of the bundle with the geometry. So there is something that could provide an extra constraint now on our deformations, because this needs to be preserved. And if we analyze this, then we see that we can write this in terms of this. The constraint on the deformations is given here. Now, using the Bianchi identity for the curvature f, one can show that these maps satisfy, or this map here, f, which is the linear map I talked about before, has to satisfy this constraint here. And this means that this is important, because this means that this map is a good map in cohomology. So it maps exact forms to exact forms and closed forms to closed forms. If we look at this constraint here, we see that the vector bundle moduli, they are not really constrained by this, because they anyway have to satisfy that this thing is 0. So we still will have the H1 and VPs. However, the geometric moduli are now constrained, because these deformations here have to live in the kernel of this map here. So this gives a restriction of our moduli space, which is that is the sum of the vector bundle moduli space and then a particular subset of the geometric moduli. However, this is not enough to prove finiteness when H is non-zero. So we need to take the third condition into account, which is this relation between the torsion and the Chern-Simons terms, so the anomaly cancellation constraint. Sorry, I went a bit too far. No. So what we do then is that we take the operator that we have constructed. So this is maybe something I should have done right away, but I wanted to show why it's actually motivated to do this. So we have this operator, and we let it act on Q-valued one forms, and we get this. And what one can show then is that the constraints on the moduli that follows from varying the supersymmetry constraints exactly reproduces the vanishing of this D-check operator when acting on these one forms. And the subtlety here is that the B-field variations must be included in this definition of the D-check of these variations. They have to pair up with the deformations of the geometry in a particular way. Then one can look at the diffeomorphism and engaged symmetry, and one can show that these trivial deformations can be written as D-check exact forms. So from this, that we can reformulate all the constraints on the moduli in this way, and then we see that the trivial deformations are given by the D-check exact forms. We see that now we actually can relate the infinitesimal moduli space to the first D-check cohomology with values in Q. And this is something finite dimensional. So what we see here is that by describing this heterotic system in terms of this differential on a bundle with particular properties, then we can actually define a finite dimensional moduli space. And now this finite dimensional moduli space is determined completely by this operator here that we chose. And also, since this operator has this form here, it's not very easy to disentangle this moduli space here into the various components that we had before. So what we claim is that you should really talk about this. You should have this holistic description of this system. And that's the only thing that can make sense. So the goal here was that to describe the geometry and moduli of this heterotic G2 system in terms of this differential and show that the supersymmetry constraints correspond to this nilpotency condition, and that the infinitesimal moduli can be counted by this Q-valid canonical G2 cohomology with respect to this operator that I defined, which is called DTEC. Any questions? Then we move on. So we can, of course, compare this with other compactifications, and in particular it's interesting to compare this with compactifications to 4 dimensions, which have been studied much more because of their relevance for our universe. So in 4 dimensions, this analogous study has been done. And the system here is the Strominger-Hull system. It consists of a 6-dimensional complex manifold which is conformally balanced, and this is now described by 2 forms. So this is a 3 form and this is a 2 form. And in the case where we don't have flux, this will then reduce to a Calabi-Yau, and this would be the holomorphic top form, and this will be the Kähler form. Now, for general SU3 structure, this is still a complex subform, and this is the Hermitian form. Then we have similar objects, of course. We have the vector bundle and the tangent bundle. Sorry, this should be an X here, it's a typo. And we have the flux. Now, there are many things are very similar in these 2 systems, but some things are different. So one thing that is different is that the constraints coming from the vanishing of the Gaugino variations, which are these instanton constraints on the curvature of the vector bundle. So in this case here we need to have an SU3 instanton, and in this case here we need to have a G2 instanton. In the SU3 case, this decomposes further. This decomposes into the condition of having a holomorphic Hermitian Young-Mills equation. And the condition of, as you might remember from Lara's talk, the condition of holomorphicity can be turns into an F-term condition in 4 dimensions, and the condition of the Young-Mills condition of the Hermitian connection is a D-term constraint, which is related to stability. Now, in 7 dimensions, we do not really have this decomposition, so the only kind of constraint we have is similar to an F-term constraint. So all the constraints on the bundle are really merged into one. So the 2 different constraints that we have in 6 dimensions, if we would embed this in a 7-dimensional manifold, this would be just then merged into one condition, which is the D2 instanton condition. So this is a difference. Apart from this, a similar analysis can be done, and so there is a nilpotent differential. It's now a holomorphic differential on a bundle which topologically can be written as a sum of various objects here in 6 dimensions. So we have the holomorphic part of the cotangent bundle, we have the 2 endomorphism bundles, and then we have the holomorphic part of the tangent bundle. So also here you see that there is a difference, that here we have this holomorphicity, so the complex structure that we have in 6 dimensions allow us to have a finer description of this kind of bundle that we have. And this is rather important, because this means that the the operator that you would write down in 6 dimensions is upper triangular, whereas the operator that I have written down in 7 dimensions is not. So this is I had entries more or less everywhere in this matrix. And in 6 dimensions, the fact that this is an upper triangular operator means that one can rewrite this bundle, so if I would call this bundle Q as well, one can rewrite it in terms of a short exact sequence, and there is a description in terms of a holomorphic courant algebroid, and this connects to generalized geometry. So there's a very interesting story here, which we do not manage to reproduce in 7 dimensions using our differential operator. However, I should say here that there has been other interesting work in this field, particularly by Clark, Garcia, Fernandez, and Tipler a couple of years ago, where they used a different technique to show that the moduli space of these compactifications is finite. And here, using their techniques, they did not manage to write down this operator, but there might be ways to connect to this 6-dimensional story that we have here. Okay, so this brings me to the last part of my talk, and maybe I'm more or less out of time. How much time do I have? Okay, very good. So now I want to think a bit freer about this. So we have determined what the moduli space is, and I want to see if we can take another perspective and learn some other things, and maybe be able to promote this study a bit further. So the perspective I want to take now is to think about this finite dimensional moduli space as a particular sublocus in this infinite dimensional parameter space. And this sublocus is specified by a superpotential that I will try to find. And the strategy here will be familiar to the physicists in the audience. The idea here is that you start with a 10-dimensional theory and you perform a dimensional reduction, that is, you integrate over your compact space. And in this dimensional reduction, what you're interested in is to identify the 3-dimensional gravitino mass, because it's known in supergravity theories that this 3-dimensional gravitino mass is related to the superpotential in the following way. So it's proportionate to the superpotential, and then with a function here which is called e to the k, and k here is the Hessian of the metric on the moduli space. So what I will do, the strategy is to perform this dimensional reduction, and then I will check that the object that I define that I identify from this process, that its variations follow from the supersymmetry constraints on the heterotic G2 system. And then I will use that to argue that then the second order variations will give me the equations of moduli, and then I could go on to higher order deformations of this superpotential to explore different things. So what do? We start from the fermionic part now of the 10-dimensional heterotic supergravity actions, and in particular we look at the gravitino terms. So here we have the gravitino, and there are 3 such terms in the 10-dimensional action. And they are contracted in various ways with the 10-dimensional gamma matrices, and then there are operators, differential operators acting on these. So there are 3 such terms here, and all of them will give contributions to a part of the 3-dimensional action which captures the mass term of the 3-dimensional gravitino. So what we need to do now is to perform this integral and identify what this term is in the 3-dimensional Lagrangian. And this is rather straightforward, but what one needs to do is to make sure that the field normalization is correct, so that in the 3-dimensional theory, the Einstein-Hilbert term has the right form. And then one has to decide on which conventions to use for the gravitino mass in anti-de Sitter spaces, because these reductions here can lead to 3-dimensional theories with either zero or a non-zero cosmological constant. And if we have a non-zero cosmological constant, this would be negative, and we have ADS. And there are two conventions that one can use for the definition of the gravitino mass. And I will choose the convention where supersymmetry implies that the gravitino mass and hence the superpotential vanish. So, what do? We decompose things. So the 10-dimensional metric is decomposed into a 3-dimensional part and a 7-dimensional part. And there is a conformal rescaling here, which I will use in order to get the right Einstein-Hilbert term. Then I have the 10-dimensional gamma matrices, which decompose, and the conformal rescaling here follows from the conformal rescaling of the metric. And so we have the external ones and the internal ones. And then we have the 10-dimensional gravitino, which decomposes into a spinner, internal spinner, and then the 3-dimensional gravitino, which is called rho here. And here is the adjoint of this. And then we just perform these calculations. So, for example, if you start with this term here, you rewrite everything using these identifications, and then you perform the integral, and you identify the result. So here what we'll see is that we have a term which had 5 gamma matrices. We split that into 2 external and 3 internal. The 2 external ones would give us something that looks like the term we want to have, with the mass term we want to have, and the 3 internal ones will then give us this spinor bilinear that gives us the 3 form on the G2 structure manifold. So this thing that is written here in square brackets will give us this thing here. And we do this for all 3 terms that I showed, and we get a mass which looks like this. So we have a term which cares about the torsion, so it's d phi which phi. Then we have a term which cares about the flux, so it's h which phi, star h which phi. And then we have a term which cares about the whether we have an ADS solution or not. So this is a particular component of the 10-dimensional torsion, which lies completely in the 3-dimensional part of space-time. So this will be 0 if we have Minkowski solutions. And when we analyze the Einstein-Hilbert term, we also find that it's natural to identify this conformal rescaling as part of the Hessian. So with that, we can identify a superpotential which looks like this. So we have the internal flux on the D2 structure manifold. We have the external flux H, which is related to F in this way here. And then we have a part with a torsion. And then we go on. So we perform a variational analysis to show that this indeed reproduces the heterotic G2 system. I just want to give you a glimpse of that. This is the variation that we write down. And you can see that if we write down the variations of the H field using this definition in terms of the anomaly cancellation condition, then we quickly see some of these constraints that we recognize as supersymmetry constraints. So here we have the fact that we have to have an integrable G2 structure. Here we have the facts that we need to have instanton bundles. And then these remaining constraints here will give constraints on the remaining parts of the torsion. And one can show that this exactly reproduces the constraints that I showed before, plus the condition that W has to be 0 at the critical locus. So this brings me to the conclusions. So what I've tried to convey today is that we can use the heterotic string compactification as a way of understanding the geometry and moduli of certain 7-dimensional manifolds with G2 structure. And what I've done is to reformulate such heterotic compactifications in terms of a nilpotent differential. And I've shown that if I do that, then I can describe the infinitesimal deformations of the system in terms of certain cohomologies. And there is also a way of describing this in terms of a superpotential which captures the same information. So the outlook now is that there is still a lot of work to be done. It would be very interesting to look at examples here. So I haven't said anything about examples. And so there are examples of these heterotic solutions. So we have so this first one here by Fernandez and collaborators is a solution of the heterotic system with non-zero H flux. So this is the integrable G2 structure with G2 instanton and flux. And so this is an example of that. And then there are also examples and constructions, I list here a few, of G2 instanton on G2 holonomy manifolds. So these, it would be very interesting to look, and this is something that we do, to look more carefully at these examples and try to compute these cohomologies and see what they actually are. Then, using this superpotential, the main reason why we did this was that we wanted to connect this to the study of invariance using the techniques of Donaldson and Segal. And what one can show is that the superpotential that I wrote down can be, if we expand it to higher orders, then we will have a term here which will contain this D operator that I have constructed, and then these are now the variations. And this term here looks, it contains, in particular, the action that Donaldson and Segal used to quantize and then to analyze invariance on the Donaldson-Segal invariance. So it would be interesting to see if one could use this description here in order to perform the same analysis. Then there are other questions that we would like to explore. Can we say something about the structure of moduli space? Can we say something about higher order deformations? Can we go to discuss finite deformations? And can we connect even better to the SU3 structure, so the Strominger-Hull system in 6 dimensions? So these are all interesting avenues to explore. And with that, I thank you for listening.
Okay, there should be time for a few questions. Okay, there's a question over there.
So you have mentioned something, you have said something about an exterior H flux.
Yes.
So what is that exactly?
So what I meant was just in these compactifications, the 10-dimensional three-form flux can be decomposed into an internal piece that is on the G2 structure manifold, and then an external piece. And since we have a 3-dimensional space now, we could choose this 3-form to be completely in this 3-dimensional space without breaking any Lorentz invariance. So this is the external piece of the H flux that I was talking about. Thanks for the question.
Okay, any other question?
You mentioned the Spark-Riemann equation.
Yes.
So if you write down that third order term that's hidden at the moment, does it have some interpretation as products?
I do not know. It's the thing we want to understand.
Thanks.
Any more questions? Okay, if not, let's thank Magdalena again.